Hi everybody. My name is Pak Lui. My role in HPC Advisory Council is to work on the application performance and basically to show some of the performance that on some of the open source and commercial applications, and to write reports and best practices to show how would be and what would be the best way of running the application. So in this session, I'm actually going to show you, some of the work that I did, on a couple of applications. So we can all benefit from looking at it. And I believe, like tomorrow, there's also a session on the application performance on the CAE applications, which is done by Science and Computing AG. So my topic will be kind of similar to be the one for tomorrow. But it won't be by me, but it will be by another person. So, okay. So this shows you, I guess, a number of performance benchmark that we've done, over the last few years. So we have different kind of applications like CAE applications, molecular dynamics applications, and weather forecasting applications. So they're actually being used in different areas of science and computation simulations models out there. So if you're interested, you can actually go to the URL right here. Okay. So first, I'm going to show you the agenda for right now. So for this session, so I'm going to do a quick run through of the overview of how to get the HPC application performance, and then the way to inspect and profile. I'm going to show you a few of the tools for doing that. They're among in different areas, like in CPU memory, in file I/O, and also for the network area. So I'm going to briefly talk to you about some of the tools that I've learned to use, and then and also going to show you some of the system configuration and tuning that I've done on a couple of applications. One of which is well-known CAE applications called Lsteiner, which is used mostly for the crash simulations, which is a CPU-based application. Another one is called HomeDBlue, which I'm going to describe to you later on about, because this is a new code that is a complete revamp of the MD code that's written exclusively on NVIDIA GPUs. So and then finally I'm going to conclude with some summaries. So some of the application performance work that I've done is to basically show how would be what would be the best way to actually get the best performance numbers that on a given system. So in order to achieve that scalability performance or that performance for the HPC workload, it involves a few things, right, that I learned throughout all this time I'm running applications. First of all, we kind of want to in order to tune for the best performance, you kind of want to understand what's going on in the application. So my personal pick would be to run through a profiler and to kind of understand what would be the most time-consuming part in that application, so you can best tune for that particular workload or that application. So throughout all this time, I actually have different profiler and analyzing tools that will run on CPU and also run on network I/O and also run on the on the network or MPI. Another kind of underlying implicit requirement is that each one of the nodes. Whoops. Something just dropped. Anyway, one of the implicit requirements is to have all the nodes to perform similarly. So this is, I guess, it's like a no-brainer, right? Because in order to get good scalability performance, you kind of want that each one of the nodes to run at the same speed and the same way. If you've got one or two of the outliers that are actually running slower than the rest, you actually have a big impact on your application performance. So we have tools for doing that, and then we have like what I typically like to do is to run something like some CPU memory tests and network tests, and Intel has their own cluster checker for doing to weed out like some of the bad systems in the cluster. So the third thing it will be to compare different kind of hardware. So in order to find out what kind of hardware would be the best to run for a particular workload. So imagine like one HPC applications like driving like a Formula 1 car. Like you have your engines kind of like access the CPUs. So if they run at higher speed, it will get you good performance, but not for every workload. So for workload, I will compare that in that F1 is to be something like the race course. You have different, you have different input data that actually that the driver would need to maneuver in a different way. So the input data actually also could make a difference too. So in this analogy, basically what I'm trying to say is that so by comparing different hardware components, you kind of get a sense of where the bottlenecks are. So I'm going to show you a few of those like comparisons so that you actually can see how effective of using one kind of hardware will have a big impact on the overall application performance. So basically, that's what I'm trying to do is to kind of demonstrate by doing a suite of MPI profiling and also some other profiling and analysis, so that to identify some of the hardware and also software bottlenecks are, and finally I would show some of the effectiveness of doing that on the real benchmarks. So as I told you before, actually here's the list of the tools and benchmark, micro benchmark that I would use to kind of find out if the behavior of the job is actually with what I'm expecting, or the overall cluster is behaving, right? So for the CPU side or the GPU side, or in general the CPU memory, so we can use tools like TOPS, HTOP, and PerfTop, and PStack. For NVIDIA, you have Prefissure Profiler, so you can kind of get a sense of how the time you actually spend inside that simulation or computation, right? So as for the micro benchmark or the that you can use to kind of identify which machine in the system actually misbehaving, or you just want to get a sense of the overall performance on the CPU side, you have something called like like Limpack HPL, and then Stream for memory throughput. As for file I/O, we have something called IOStat and Collect L, and then Dashen. So we basically showed you some of the sensitivity of the I/O or the disk I/O that you have, and then for network part of it, we have something for the MPI side like IPM, Tau, and some other ones out there. So and then we use something like OSU benchmarks and IMP to kind of identify if they are the network throughput. So these kind of tests are actually just what we call micro benchmarks. So they may or may not have direct impact on the real application. It really depends on how the application code and actually use on this kind of like hardware in order to translate right into the real application performance. So benchmark can do one thing, right, and then application can kind of behave the other way. So by profiling, you actually can see how much of the time actually spent on doing computing, I/O, and so on. Oops. So first case study that I'm going to do is called Lsteiner. So I'm pretty sure many of you have heard at least, or if not used already. So Lsteiner is developed by the Livermore Software Technology Corporation in California. So it's basically a well-known like general purpose structure and fluid analysis simulation package. So mainly used for crash simulation, that's what I know. So and then the objective of this is actually we use this software and also application, this input data set, in order to kind of to show how sensitive are they for CPU memory side, and then for MPI side, and also for the interconnect part of it. So I'm going to talk to you about that, those areas and the sensitivities of them, so we can see where could be the bottlenecks of those hardware or something like that. So before I dive into that, so this I want to show you the type of system that I'm using. So I'm using a Dell PowerEdge R720XT cluster, or 32-node cluster that we have at the HPC Advisory Council lab. So the lab is actually located in Sunnyvale, California, in the US. So we're using the Ivy Bridge CPUs, with the turbo mode enabled, but I'll also show some of the tests actually done with the turbo mode disabled, so they can see the effect of it. So here's the rest of the configuration. It's using non-SOFED, the latest one, and then it's also Intel cluster ready certified. Means that the good thing about Intel cluster ready is actually it helps checking the cluster to make sure that each one of the compute nodes actually behave somewhat similar across the board, so that in case you actually trying to test for scalability, actually would be very it's very important, because you actually want to have have a baseline so that every node actually behave similarly, right? So we also compare different kind of MPIs in here. So we're gonna show some of the comparison over here. And then, so the free vehicle collision and the neon device benchmarks are shown, will be shown. So this is another slide on the Dell cluster that we have. So it has plenty of drives per node, but it is also very efficient, because in a way that it's a 2U box that has many different PCI slots, so we can do a lot of testing with it. So first comparison that I would like to do is focus on the CPU side. This is when the turbo mode is enabled. So turbo mode, as you know, is actually would allow the CPUs to dynamically clock up to a level that actually would be still safe to operate. But it also depends on the environmental part of it, meaning that the system temperature, it will not exceed its safe limit. So by clocking up directly using turbo mode, we actually can see a benefit on the application performance. But at the same time, you also can see that there are also more power is drawn for turning up the turbo mode. So we see quite good improvement on with turbo mode on, but at the same time you actually spend would cost more power actually to be drawn by having turbo mode on. So in here we actually see that about it's an increase from 320 watts to it should say watt right here, so typo right here, but to about 380 watts on one node. So we have not done for a whole cluster-wide measurement, but this is a ballpark. So similarly, this is one of the questions I get asked once in a while, is to see what would be the more preferred configuration for memory. So for memory, for this particular system architecture for Ivy Bridge, we have the choice for using a single rank memory, and also a dual rail memory with a slightly lower speed. So what we have found is that using a single rank memory that has like a slightly faster rate, the 1866 megahertz is actually showing less performance than the dual rank. So this is actually kind of interesting to show, and I only do it have enough things to do on one of the nodes. So continuing on. So for this application and also this input data sets, we know that for Lsteiner and free vehicle collision, the I/O part of it is actually should not be great. I mean, it's not great, and I'm going to show you in a subsequent slide. from the I/O profiling, and also the measurement of the writes and reads and for each of the compute node. But we know that I/O is not a big part of it. But what I've seen is that in this case, even on the I/O component is not writing and reading a lot. The performance difference by using an NFS mounted directory versus like writing on a local shared memory, you actually can see a huge performance difference. So up to around like 22% of performance difference by using a shared memory to write. So this is one of the ways that actually can improve performance, but I would not call it like the preferred way of for all you guys to start writing into your shared memory, because this is really not a safe way of writing, and it's not it's not ideal for a production environment. It's just to test the importance of having good parallel file system, like some of the vendors right here, like Cyratex or DDN, they provide like good lustre parallel file system that actually can allow you to have good parallel reads and writes. So we really advise you to write on a custom file system instead of temporary storage. I'm only doing this because at the time I was running this, I would not have a good parallel file system that's available to me. But so this introduced you the I/O profiling collection tools that called Collect L. So Collect L is called Connect for Linux. You can get it from this URL right here. So this is the example of how it's run before. So as you can see, there's some of the outputs from here. So it basically writes how many, it do a 1 second increment on data collected. So every second it print out one line about how much each of the, I guess kilobytes of the writes and reads that it sees, the system basically detects. So by doing that on each one of the nodes, and I kind of get a sense of how much of the write that for this particular benchmark, and on this for this workload. So for the node Windows Rack 0, you see it's a spike right here at the beginning of the run. As for the other nodes, you kind of see the similar things, but you know that the data writes actually on this scale is actually not great, even though it actually happens on all the compute nodes altogether. But the effect of it when all the nodes actually doing it at the same time, you actually see a big impact as what we have seen right here. So up to 22% when all 32 nodes are doing at the same time, right? So this is for the node with rank 0, and this is for the rest of the cluster node. So the behavior is pretty much similar. So let me dive into the interconnect part of it. So in here, I'm comparing a different kind of network interconnect. So we have 1 gigabit Ethernet, which is readily available on each of the compute node. So 1 gig E, and then we have 10 and 40, which is adapter from Mellanox, and then we also have the FDL InfiniBand as well. So we are comparing different kind of network interconnect with respect to their scalability. So we can see that from InfiniBand, for InfiniBand, right? So the scalability continues to grow. As it scale, from 8 to 16 to 32. As for the 10 and 40 gigabit Ethernet, so they're kind of using the same technology, so their latency pretty much the same. So therefore you actually can see that the performance differences is very minimal, right? So you actually don't see much of a difference. So compare 1 gig E with with InfiniBand, you actually cannot compare. So you probably would not want to use anything like for 1 gig E beyond 4 nodes or so, because the performance actually would drop because there's too many traffic actually taking place on the network. 10 and 40 gig E, so they actually would also scale, I'll say backward after 16 nodes or so. So if you actually have to run any sizable simulations, you definitely will going to use for InfiniBand. So some of the MPI tuning that I was able to do with this is shown right here. So I included the MPI command line options, so in case that any of you is interested. So So this is showing you something called FCA and MXM in here. So FCA is some technologies developed by Mellanox for doing fabric collective acceleration. This is actually taking place in the hardware, in adapter, and also on the switches. So it's about like being able to use the hardware for doing like multicast, and also it helps doing MPI collectives. So it will only be beneficial for any application that uses collectives, such as BCast, barrier, all gathered, and reduce, and things like that. So if you have applications that don't have, from what I've seen, is that if you have applications that don't use any collective at all, so FCA would not be beneficial to you. MXM is a way of like doing send and receive and tag matching. So it actually is a messaging acceleration on top of the what's running in OpenMPI. So as you probably know from OpenMPI, there's something called OpenIPBTL. The OpenIPBTL is responsible for doing like messaging, but to get the hardware acceleration, MXM is really what Mellanox has actually put in recently to accelerate those kind of messages, and you can actually pick the type of the transport that's available for MXM. So in here we're using the UD, the unreliable diagram for doing messaging. So with those two acceleration software being used, we actually see a much better performance improvement at 32 nodes. But how does it really compare when you take it to other MPI implementation, right? So in here we're comparing that those used in they're just showing you in OpenMPI with a couple of commercial MPIs, so which are platform and Intel MPI. So, and also I listed some of the performance tuning that I did for those two, right? So for OpenMPI, as what I use is FCA and MXM, and also KNEM. KNEM is the internode optimization, and also bind to core, because OpenMPI historically does not bind the processor to the core. So you actually have to specify for platform. Similarly, but only XRC is available for them. So Intel MPI, I use the IB verbs transport for it, and then also there's something to make it run a little faster, as what I'm showing here. So we see that it's a good improvement for platform compared to others. But OpenMPI with the tuning, you're able to see some benefit as well. So this is also very important, because like you don't necessarily need to get commercial MPI, to get very good performance. You just need to make sure that your application is run with the MPI that's tuned properly. So this is an interesting slide. It basically compares different generations, I'll call, of systems to the current generations of the system that you get with the latest hardware components. Right. So those four that I'm showing right here is that they are at the time the typical HPC configuration. They're not very. They're very typical ones that people would use for running the jobs at that time. So when you look at the Lsteiner bridge technology, and all the different hardware components that's available in the Lsteiner bridge era, and you run Lsteiner with it, so this is the performance you get in the blue bar, right? So, and then you take the Westmere generation of the cluster and mix it with using the same memory and network technology, and that's what you see in the green bar. So etc. So when you take the recent 4 generations of the Intel technologies that are out there, and you see that that's not. I mean, running with the current generation will actually get you the best performance, right? So, but you also can find out is that when you are a couple of generations behind and you're running Lsteiner, Lsteiner is is a compute-intensive application, right? I hope you agree. And then you kind of see that, with the latest like Ivy Bridge cluster, then you say you get 8 nodes of it. So you actually would be, better off than what you had like 2 years ago at 16 nodes. So it actually gives you some justification of, you're using cluster for, and it also included all the power that you use, and then you actually don't get a lot of benefits of the performance if you're still using a cluster that kind of like a few years back technology. So this actually gives you a perspective. I would not call it this is the hard results that you will get, but it's just like a good estimate of where we are using the new technology versus the some of the old technologies that are out there. With the latest like cluster configuration in CPU and in network, and with the MPI tuning, we're able to see very good performance like that we compare to what we can see from the top branch benchmark. So here's the numbers that we're able to show for the benefits for the improvement, I guess, compared to what was existing top crunch numbers on that website. So at the time when I did that, so at the time probably some of the entries actually were not the latest, but we can see that with the current generation of system hardware, we're able to see good performance compared to what was available at the time. And this is one of the observations that I see by running something like 2 jobs in the same time. I don't mean running 2 jobs at the same time, but it's more like running jobs that are actually using the same set of computation resources. So let's say you have, I'm actually comparing. Take this example, right? So at a 32 node case, I have 1 job running all 32 nodes and using all the cores on those like 32 nodes, and this is the performance I get, right? And if I take those 32 nodes and I only use half of the available cores, and actually what I meant is this one. If I take 2 jobs running in parallel and use half of the cores available on those systems, I'll end up getting much higher performance right here. So this is an interesting observation because many of the HPC jobs that we run, we pretty much dedicated the entire set of nodes that we use for one particular job only. But if I just split it up into running on the cores, actually allocate on one side of this one side of the CPU for one job, and then the cores on the other side of the CPU for another job, you seem to get better performance. So this is an interesting observation. So just want to point you out to that. So in here, I'm showing you some of the notes I have for doing MPI profiling. I find IPM is useful in a way that you don't necessarily need to recompile the code, especially when you try to do MPI profiling on a commercial application when you don't have the code available to you. So running with IPM, you only need to do LT preload to load that module before the MPI run command in order to generate a report from it. So we actually show you what are the message sizes, what are the block sizes that should be used, what type of MPI calls were being used, and things like that. So those are pretty interesting if you kind of want to understand why my network interconnect has no effect or has a lot of effect, on a particular application or workload or interconnect. So or workload. So this will be a really good way of showing, of understanding the application as far as the communication goes. So the subsequent slides are what I've seen from kind of profiling those MPI codes, and these are graphs that actually just plot it with Excel and show it. So as you can see, with more and more nodes being involved and using an InfiniBand cluster, we see that more and more of the time actually, more and more time actually is being saved by having more nodes being part of the cluster. And then while the MPI time would drop a little bit, but stay pretty much flat. So as you have more and more system being part of the cluster, it actually improve on the time that actually spent on computation, right? So this is no surprise, but it was actually good to point out. Here's another slide on the type of the MPI calls that I find out from the profiling, right? So this you can see how many calls actually been shown for being used in this application for this particular input data. So MPI wait all seems to be the most, and then followed by MPI send and MPI I receive from a blocking call. So that is not very interesting, but this is a little bit more interesting because it actually tells you how much time those MPI calls are spent, right? So with the FDR InfiniBand cluster running on 32 node, we see that the amount of time actually spent on or reduced actually would actually keeps dropping. So this is a collective operation, and then so for BCAS as well. So those two are the collective operations, meaning that all of the nodes and all the processes actually, all the MPI ranks would also have to be participate in that area, that kind of network transfers, as opposed to like receive, which is just point to point, but communication. So this is important because to understand the importance of this is because because as I've shown you earlier, I mentioned FCA, right? So FCA is the fabric collective acceleration. You only have the effect on these two calls right here. So as for the blocking or receive, it would not. FCA has no effect of it. But having a good network interconnect would have effect on this part of it. So and the latency actually would improve on those two. This is yet another slide on the profiling that I see on the 3 vehicle collision data sets. So we see that a large concentration of the small messages are being used. So mostly concentrate on really small 0 to 64 bytes. So typical HPC workload and communication kind of like happening right here. So having a low latency interconnect would help. So InfiniBand is being one of them. So MPI receive is really taking place in the 4 bytes right here. 4 kilobytes, I'm sorry, right here. So I guess it's somewhere right there. So I definitely, if I have to do it again, I probably would reduce a lot of other lines right here because it's kind of hard to show. But this gives you a really good overall picture of how much of the communication actually taking place for Lsteiner, even for the benchmark like this. So for this one, it shows you how much of the MPI data transfer per rank. So starting from 0 rank, you see it's a big data transfer actually happens for the rank 0 for Lsteiner. As for the rest, there are some, I would say, imbalances, but it's actually not because it's just the way that that Lsteiner handles the communication. But the imbalance actually more happens in the rank 0. So because it seems to show that a lot of data transfer is taking place for the 0 rank compared to the rest. So that's the 32 node case. So the 2 node case, you don't see the effect that much, though. But as you scale to more nodes, that change will actually happens more, have a bigger impact. So just want to point the next slide shows the amount of data transfer actually taking place. So this slide is actually pretty much is an aggregate of the sum of the data actually for all these right here for the 32 node. So for the 2 node case, it will be right here. So when you take the sum of all those ranks and they add them up, so you kind of get a stepwise kind of graph that shows you how much of the data actually being transferred per node. So it continues to increase as you scale to more and more systems. So, and memory usage is also being part of it. It's very important because you definitely don't want to run your application with without having sufficient memory on the system per node. So the typical size for running this benchmark seems to be around like so right here. So about 60 for 2 nodes it's more like 35 I guess gigabytes. So the trend seems to be the same across for other nodes. So this is per node basis. So when you have a node that is, at least 35 gigabytes of RAM, if not, what's going to happen is that you'll run into thrashing. So it'll be really bad for your performance on the for Lsteiner. So this to summarize some of the findings I saw, and then is what we have what I've shown you earlier. So let me go ahead and talk about the other applications, which is called HomeDBlue. So HomeDBlue it stands for Highly Optimized Object-Oriented Many-Particle Dynamics Blue Edition. It's a mouthful. It basically is a MD simulation software that actually does molecular dynamic simulations. It is completely rewrite of the existing code for NVIDIA GPUs. So I recently have worked with the HomeDBlue developers on running it on the GPUs to kind of demonstrate and also to find what would be the best way of running it on the GPU cluster. So, and I'm going to share with you on the subsequent slides. So it's a free open source code, and then you can actually just download and run. So I work with like Jen Glaisler and Joshua Anderson from the HomeDBlue project. So they are the guys actually leading to for this for the GPU port. So here's just some of the information about HomeDBlue and where you can get it down right at the bottom. So it's the I'm cited their work right here. So, and I'm also going to show you some of the performance numbers that I got from the University of Cambridge cluster, which is which I'm going to show you some of the performance result over there. So this is similar objective as what I'm showing before. The idea is to kind of want to show you some of the performance differences by using different hardware, and also some of the MPI performance improvement by tuning over there. This describes to you the first configuration that I used. This is also on the same cluster that I used before, but this time I'm using it with the NVIDIA K40, the latest GPUs. The rest of the setup are pretty much the same because it's this is the same on the same cluster that I did. And besides OpenMPI, actually this right here, I'm also using the latest InfraPitch 2.0 GDR beta. So I missed putting it right here. And then the benchmark I'm going to use is called the Lennard-Jones liquid benchmark, and with that particular particle sizes. So let me first describe to you the Mellanox GPU Direct RDMA. So you probably have heard from Dr. D.K. Pender had mentioned earlier. So GPU Direct RDMA is like a project that that has been worked on by NVIDIA and also by Mellanox side, and also by OSU and for different MPI implementation, to take advantage of having reducing the amount of extra memory copy that needs to happen on the system host side, right? So with the latest GPU Direct RDMA, what's happening is that you actually can actually communicate your GPU device right here through the PCIe bus to the InfiniBand adapter without having to do it with anything that happens on the CPU side. It actually helps because writing back and forth the GPU and the system host memory is really costly. It takes a long time, and then the gpdirect RDMA would actually just bypasses that CPU, the host memory side altogether, and then use the pin buffer on the GPU instead on the other side to write and read. So this actually eliminates a lot of bottlenecks, and if the application does a lot of transfer to other systems. So HomeDBlue is actually showing this some performance difference. So I'm going to show you that too. So this is a really new technology that's out there. So it actually has a significant impact. What's important is actually this technology currently works for the MPI send and receive one-sided communication, so to improve the performance of it. So in order to use gpdirect RDMA, there are requirements that you need to do. So as previously mentioned, I think so there are like a few prerequisites, right? So you need to get the XML on SOFET, the NVIDIA driver, so that it has the support. The CUDA toolkit 5.5 would have supports. If not, then you can also use the 6.0. I think there's like an early access version that's out there right now. And also finally the heart of the the heart of the gpdirect RDMA is called the MD peer mem. This is a kernel module that actually allows gpdirect RDMA to take place. So all that information are here. So I'm showing you a couple of the MPI that currently have the support for gpdirect RDMA, right? So Anthropage to GDR, from Dr. DK Penna's team, currently has a beta version that actually supports gpdirect RDMA. So the requires parameters are actually shown here. So you need to set these two parameters on the left in order to enable gpdirect RDMA. And then there are some optional tuning parameters that actually would allows you to either specify which InfiniBand adapter to use, and also what is the limit of the message size that actually would allow gpdirect RDMA to work, right? So on the other hand, for the OpenMPI, starting with OpenMPI 1.74 RC1, it starts to have the gpdirect RDMA support as well. So you kind of find the same similar parameters that need to set, and then their default is 3 kilobytes, 30 kilobytes of size is when the cutoff starts to happen. So there's a limit. It's called the cutoff, the threshold. This is when you're below that threshold, you'll use gpdirect RDMA. When you're above that, you'll become like a asynchronous, send and receive through rendezvous protocol. So there's a cutoff that was able that you need to decide if you need to tune for a different limit. You want to adjust that limit, but in order to understand what would be the best number to tune, you actually kind of want to see from the MPI profile what are the typical, or what would be the most of the concentration of the send and receive messages happens. So I'm going to show you that in a few slides right here. So the first example I'm showing you with the gpdirect RDMA is on a small cluster. So I'm pretty sure that many of you have started investigate on the use of GPUs, and you want to see if they will be beneficial for using gpdirect RDMA, right? So even with the small cluster like 4 nodes, I was able to see some benefits of using gpdirect RDMA on a given workload. So on a 16K particle size workload, with GPU Direct RDMA, I see about like 20% improvement, so which is great, because what actually happens is that if there wasn't a GPU Direct RDMA being used, you kind of get limited scaling. Get pretty flat scaling at all. I mean, there's not even any good performance when you're using 2 or 3 nodes or 4 nodes. So if I started to run on a larger particle size case, the scaling would actually happen, but with GPU Direct, I'm able to see much better performance as well. So up to like 10% at 4 nodes. So this is done by OpenMPI for this case. So and to understand what would be the best way of tuning that parameters, you actually need to set it like that. And first of all, you need to do a profiling of that. So I think I may have a slide that talks about it, right? Yes. So first of all, for the 2 cases that I show you in the previous slide, so I have the 16K particle and then the 64K particle sizes. So in here that I was able to find out is that the MPI I send and I receive and where those concentrations are. So if I know that about like 95 or 100% actually of the message sizes actually taking place right here, then I would need to adjust this the GPU Direct RDMA limit for that size, because what happened is that after that limit, GPU Direct RDMA is not working. It's not going to work. So you actually would want to just adjust that the limit right here. So for OpenMPI, the default number is 30K, as I mentioned, 30K kilobytes. So what I ended up doing was to adjust it to around 64K, to show the performance that I was able to see from here. So 64K is what I did for the 64K particle size. So a bit of the MPI profiles actually would help you to understand what's going on in the back end. So to improve the performance. So I take it a step further and then try on University of Cambridge cluster, because I know that they have a much bigger cluster out there, so 128 nodes with the NVIDIA K20 GPUs. So K20 GPUs are low, this is not the latest from NVIDIA. This is Gen 2 GPUs as opposed to K40, which is the Gen 3 GPUs. So, but anyway, the effect was actually kind of similar. If you just take away the extra performance out from the K20, you see the effect of GPU Direct is actually similar. It will perform similarly. So I listed out some of the characteristic of the cluster configuration right here, in case you actually want to visit some differences compared to the ones that I showed you earlier. Mainly it's just that the GPU is a little different because the majority of the computation actually happens on GPU. The CPU is a little slower because this is a GPU only, well, it's a GPU cluster, so not much of the computation power is actually coming out from the CPU side. So that is understandable. It really has very little effect on the performance for this particular GPU application, right? And then the data input data size actually I'm showing right here is a much larger one because I actually do want to show some of the performance like at the scale. So. So here's another introductory slides for the wheel cluster. This is the name for the cluster at University of Cambridge. So it's the second most energy efficient in a Green 500 list. I was told. So this is a collaboration of Dell, NVIDIA, and also Mellanox. So it is deployed in a few months ago. So in November 2013. So I'm using this actually to demonstrate the benefit of using gpdirect RDMA. So this I probably have described to you earlier, so I may be able to skip it. Right. So for the subsequent slide, I'm going to show you some of the performance like comparison. And first right here, I'm going to show you the flag that I use for running those tests. So I worked on this project with Filippo Sbrigga from the University of Cambridge. So I'll give him, I wouldn't mention his name because we worked together on this. So the letters actually shown on the red is basically the flags for showing for picking the right interface. So in case that you have multiple interfaces on the system, so this is what you need to adjust. And the letters in green are the ones actually showing you not to use not to cross over the QPI bus. So because this actually has some performance impact on it. So this is the performance I see for using gpdirect RDMA. So what we can find out is that it actually allows better scalability performance improvement. So about like double of the performance you can see from not using gpdirect RDMA for the big particle size simulation that we do for the 512K particles. So the benefits actually start picking up around like 8 nodes and so on, because it's just the way that we start seeing. So without gpdirect RDMA, you actually see not a good scalability up there. So this is I'm going to show you this in subsequent slide on the similar profile that I showed you earlier. This is a good slide because they actually show you. So no matter the application or the input data would stop scaling, gpdirect RDMA would still provide you a benefit, right? So there are cases that, up to a point that the application will no longer scale because there's not much benefits of using more system or more GPUs for this, input data, because the input data was not able to saturate for all those system resources. The extra system will become the node overhead. Right. But in any case, we can actually see that if you have more and more systems, gpdirect will always give you a better benefits. I mean, better scalability at a higher node count. To give you a perspective of how the performance lag on the wheel cluster compared to other cluster out there. So this is the results I received from the HomeDBlue developer comparing to the Oak Ridge Titan cluster that they have that they also are working on the side. So Titan is using the K20X GPUs, which runs at a really higher computation rate and then on the Wilkes cluster, which is running K20. So you can see the effect of it from the 1 and 2 node and probably 4 node case that the Titan clusters actually performs higher than what I did on the Wilkes cluster. So with the gpdirect RDMA enabled. However, that effect actually would kind of would disappear, and then the Wilkes cluster actually would perform much better compared to Oak Ridge results that we found. So it actually shows you that with gpdirect RDMA enabled, you are seeing much better result. And for something that actually did not think, the developer did not think that they would scale up to 6 node and 32 node on Titan, we actually can provide higher scalability, much higher scalability than that, and with the gpdirect RDMA. So this is a good example that we can that want to highlight. So MPI is also very important. MPI, I know that the teams in Interconnect 2 and GDR, and also for OpenMPI, they worked on a lot in providing this support. So currently, I know that both of them actually are still in the still on the improving stage. But this will actually give you a really good perspective on how the performance difference, or if there's any on the different on the workload. So both seem to perform similarly, but there are some cases that gpdirect RDMA for both of them would be different. So both have the support for gpdirect RDMA. OpenMPI seems to show performance better at some cases than Interconnect. So I just want to point out to that. I think we're running out of time. Let me skip that and go on to some of the MPI profiling. So we can see that for the 4 node 512K particle size that I showed you earlier, Many of the time actually spent in wait all. So the behavior is actually different that you scale to a 96 node. So you get much different API communication that take place. So this is another graph that shows that. The important thing about the GPU Direct RDMA, I probably have told you earlier, is that it will improve the messaging that actually happens for non-blocking send and also non-blocking receive. For something that actually take place that in all-to-all and other API collective operations, it will not have any effect. So for GPU Direct RDMA, it's very important that that you look for the API send and receive, I send and I receive, that they will be able to take advantage of. And then you want to make sure that for OpenMPI at least, the 30 kilobytes of the messaging window needs to be adjusted by using profiling. So that's what we can see from here. So by adjusting this, you should be able to capture all the benefits of using GPU Direct RDMA. Here is another profiler's outputs from IPM. So this shows you the amount of data actually being transferred per node-to-node basis. So you do see that there are a lot of data actually being transferred. And then it's just basically the summary of the findings that I've seen. And here's the end of it. Thank you very much for your time.
Any questions for Pat? Yes. Any estimation for Haswell performance?
Any estimation for Haswell?
Any estimation for Haswell was a question. So far, I do not have a machine to test for Haswell. So it will be kind of unfair to comment on it in case it changes. So, I mean, generally, I think it's unfair to comment on anything until it releases. Anyway, but from what I can see from, I mean, Haswell, as you know, is the next generation of the Intel CPU architecture. So after Sandy Bridge and Ivy Bridge, the one that's supposed to be coming out from later this year, I guess, is called Haswell. So I personally don't have hardware for testing, so I cannot answer it. Even though if I have, anyway, I don't have it, so I don't know.
You can't tell.
I don't have it. Yes.